and you can go ahead. All right. I can't hear actually. Is it working for other people? There, now it's good.
Interesting. Okay. So thank you for the invitation. Um, I'd like to talk about
It
I
just
can't
stopped
hear you,
again.
Max.
It stopped again.
oh, that's interesting.
It seems to be when you lean back.
Okay, I'll try to lead forward. So yes, I'd like to talk about a very old problem, but it seems like some things are still not fully understood about it. All right. So the subject is boundary criticality. So what is this about? Well, the idea is you have some bulk system that's critical, perhaps described by a conformal field theory, and you'd like to study the behavior of the system in the presence of a boundary here. For instance, you might ask what is the um, what are the correlation functions near the boundary. And in general, the behavior near the boundary is different from the behavior in the bulk. For instance, the scaling dimensions of operators on the boundary, denoted by delta hat here, are different from the scaling dimensions in the bulk. Another comment is that this boundary universality class, the boundary conformal field theory, is not unique. For a given bulk system, there might be various boundary fixed points with phase transitions between them, and we will encounter some examples of this later in the talk. So, as I said, boundary criticality is really an old subject going back to the 70s and 80s, classical statistical mechanics, but there's been some renewed interest in it lately. One reason for that is advancement in conformal bootstrap techniques. Another reason is another motivation comes from the physics of symmetry protected topological phases. So remember these SPT phases, they're gapped in the bulk, but they possess some non-trivial, sometimes gapless boundary degrees of freedom. Now, one question that has been asked is, suppose you take this SPT phase and you drive it through a phase transition, maybe to a trivial symmetric phase or to a symmetry broken phase. And the question is, does anything remain at the critical point of the gapless degrees of freedom on the boundary? And that turns out to be a very rich, interesting question. I believe it was first posed in this paper by Tarun Grover and Ashwin Vishwanath, but there have been dozens of papers on this since. So I'll touch a little bit on this towards the second half of my talk, but actually most of my talk will just be about classical StatMech. And as I'll try to convince you, even there are still some unresolved questions. All right, so the main problem I'd like to address in my talk is that of classical ON model in the presence of a boundary. So couldn't be simpler than that. So take a d-dimensional hypercubic lattice with a boundary, and consider classical ON spins, just n-component vectors, living on this lattice, and coupled with this nearest neighbor coupling. And I'll choose the nearest neighbor coupling in the following way. When the two spins live right on the boundary, I'll set the coupling to K1, and otherwise I'll set the coupling to K. So in general, this can be different. So K is the bulk coupling, K1 is the surface coupling. Now, And I'll be interested in the phase diagram, including the phase diagram of the boundary. Now, when the bulk dimension D is greater than 3, then here is the accepted phase diagram. So the axis here, again, vertical axis is the bulk coupling, horizontal axis is the surface coupling. And okay, so Kc is the bulk critical coupling. That's when the bulk becomes critical. So for K greater than Kc, the bulk is ordered. For K smaller than Kc, the bulk is disordered. That's as far as the bulk behavior is concerned. What about the boundary behavior? Well, if the surface coupling K1 is not too large, then what happens is that as we lower the temperature, the surface and the bulk order at the same point. This is known as the ordinary universality class. However, if the surface coupling K1 is large enough, it is possible for the surface to order before the bulk orders at a higher temperature than the bulk. So then we have this phase here where the surface is ordered, but the bulk is still disordered. And well, it's separated from a high temperature phase by a purely surface phase transition. So this is here at this phase transition, the bulk is still gapped. So it's really just a d-1 dimensional transition in the ON universality class. A little bit more interesting is this transition here. This is the ordering of the bulk in the presence of a surface that's already ordered. And that's known as the extraordinary transition. And we'll come back to it in a second. Finally, there is this multi-critical point that's reached by tuning the surface coupling K1, interpolating between the ordinary and the extraordinary classes, and that's known as the special critical point. All right. So this is the standard accepted phase diagram when bulk dimension D is greater than 3. In all of my talk, D will stand for the bulk dimension. So far, I've assumed that there is no symmetry breaking either in the bulk or on the surface. However, one can also consider a surface where there is an explicit symmetry breaking field, H1, like so. So in this case, it's believed that there is just one stable fixed point, and this is known as the normal universality class. So this is bulk ordering in the presence of an explicit symmetry breaking boundary field. So that's known as the normal fixed point. For the name normal comes from kind of historic reason that I'll not get into. Now there is an interesting fact, which is when the dimension D is greater than 3, it's believed that the extraordinary universality class is the same as the normal universality class, essentially the same. That is, it doesn't matter if the symmetry on the boundary is broken explicitly or spontaneously. The boundary, the bulk ordering for the case of an already ordered boundary is the same in the two cases. In the case when the spins are Ising spins, when n is equal to 1, that's almost obvious. Doesn't matter. You already have an order parameter that acts like a symmetry breaking field here. In the case when n is greater than 1, it's maybe less obvious, but it's still essentially true. That is, the fluctuations, the extra goldstone modes present on the boundary here in the extraordinary at the extraordinary transition essentially decouple from the bulk, and the extraordinary transition is essentially equivalent to the normal transition. Any questions so far? All right. So this is the situation when dimension is greater than 3. Note, I will often treat d as a continuous variable in my talk. So what I will be really interested is the case when d is equal to 3. And here, if the symmetry is Ising, n equal 1, then the story is exactly the same. You have the ordinary, the extraordinary, and the special fixed points. But things get more interesting when n is equal to 2 or is greater than 2. So first, let's begin with the case n is equal to 2. So here, the topology of the phase diagram is still the same, with one difference. Instead of the phase with true long range boundary order, we have only quasi-long range order in this region of the phase diagram, right? So here the correlator on the boundary of the order parameter falls off as a power law, whereas bulk correlator is still gapped. So here, the surface phase transition is a just two-dimensional transition in the XY universality class, so that's understood. But what's a little non-trivial is this extraordinary transition, right? So what happens if you start in this phase with quasi-long range boundary order and go through the bulk ordering transition? And to my surprise, apparently this question has not been addressed in the literature before. The only discussion of it that I could find is in this paper by Denk, Blot, and Nightingale, and it's essentially a numerical paper, a classical Monte Carlo paper, and what they what they suggest is that perhaps let's see if I can move my what they suggest is that perhaps even though you only have quasi-long range order above the bulk ordering temperature, right at the transition, perhaps the boundary can have true long range order. That is, there can be a finite expectation value of the boundary order parameter. Well, that would essentially mean that the boundary order parameter jumps from 0 here to a finite value at and below the bulk critical temperature. The numerical data was roughly consistent with this story. So okay, it sounds kind of strange, but actually I couldn't find a way to immediately shoot this scenario down. Indeed, while above the bulk critical temperature, we cannot have true long range order on the boundary, just kind of by Merman-Wagner theorem. At bulk criticality, we have gapless degrees of freedom in the bulk. If you think about integrating them out, we get some kind of boundary problem with power law interactions. We know that even in 2 dimensions and even with continuous spins, if you have power law interactions, in principle we can have a true long range order. So it's not so obvious that this scenario couldn't happen. But indeed, it does not happen. this story is not quite right.
Max, a small question. Do you generate the winding operators on the boundary at the quasi-long range phase?
You mean where the vortices play a role?
Yeah, I don't understand that because then it would not be algebraic decay.
Right, so vortices in principle, vortices on the boundary are in principle allowed, right? And that's why when you go to high enough temperature here, the surface is disordered, as well as the bulk. However, below some temperature, the scaling dimension of the vortex operator on the boundary is going to be, become larger than 2. They're going to become irrelevant. So you're going to have usual Kosterlitz-Thouless transition here.
Yeah. Okay. So basically, you drop them. That's what you. That's then you get long range order. I see. Thanks.
I think it's a good question, but so they definitely play a role in this phase and near the transition. As you go to the extraordinary line, as you go to the boundary, as you go to the bulk phase transition, as I'll argue, they become less and less relevant. So we drop them. Yeah.
Okay. Thanks.
Right. So yeah, this scenario doesn't quite play out as I'll argue using a normalization group. Instead, what one finds is at this extraordinary line, we have an order parameter correlation function that decays as a power of logarithm of the separation, log x to q, where q is some universal number. So the boundary along this extraordinary line is almost ordered, but not quite. Correlation function decays slower than any power law. Another comment is that the stiffness of the boundary or the parameter or the Latinger exponent diverges logarithmically as we approach the bulk critical point. Right, so remember the scaling dimension of the vortices is actually proportional to this Latinger parameter. So the scaling dimension also diverges logarithmically. So it should be possible to drop them. This is in response to Zohar's question. All right, and I will refer to this behavior as extraordinary log behavior. Just to contrast it with the extraordinary transition in dimension greater than 3, where we have true long-range order on the boundary. All right. So what happens when we go to even larger value of n? So n greater than 2. So here there are two possibilities. So kind of the most conservative possibility is that, well, we know that there is no long-range ordered or quasi-long-range ordered phase on the boundary for temperature larger than the bulk critical temperature. So then it's not mandated by the topology of the phase diagram that there be separate boundary universality classes at bulk TC. It's possible that we just have only the ordinary universality class independent of the surface enhancement, K1. However, and actually I think this is the picture that that is implicitly assumed in the literature, although it's not discussed in a lot of detail. It's also, however, not ruled out that part of your phase boundary is in one universality class, the ordinary, and another part at large surface enhancement, it has some other universality class that I'll still label as extraordinary here for lack of a better name. This is still possible, even though they, the two universality classes connect to the same bulk and boundary phases. above and below bulk TC. So which one of these two scenarios is actually realized? And as I will argue, again using a normalization group, this depends on the value of n. So when n is large but finite, we have this picture with only the ordinary universality class. However, if we treat n as a continuous parameter, at least for n close to 2, we have this picture with both the ordinary and the extraordinary portions of the phase boundary, and indeed the extraordinary region is of the extraordinary log type, again with correlation functions of order parameter decaying as a power of logarithm, and the power q now depends on n. So this is the conclusion of the RG treatment. But first, let me kind of give arguments in favor of this without even doing any RG. So first, let's begin with the case when n is large. So first of all, you can do large n calculations in dimension d equal 3, and you find that when n is equal to infinity, there is no special fixed point. So if there is no special fixed point, that means that there is presumably no extraordinary fixed point either. Another way to see that there is only the ordinary transition for large n in d equal 3, or at least to kind of guess, is to go to dimensions slightly larger than 3. So in fact, in any dimension d greater than 3, we can do large n calculations for the special fixed point. So the special fixed point exists for any d greater than 3 and at large n. And well, we can do large n calculations. For instance, we can calculate the scaling dimension of the order parameter at this special fixed point.
Sorry, Max, can you remind us what is so special about the special fixed point?
There is, well,
How do you distinguish it from the ordinary one? What is the property that you're looking for?
It has one more relevant, right? So the ordinary fixed point has no relevant boundary operators.
Mm-hmm.
The special fixed point has one relevant boundary operator, and it separates, in d greater than 3, it separates the ordinary fixed point from an extraordinary. Extraordinary is when you have spontaneous symmetry breaking on the boundary. So essentially, bulk order parameter mixes with identity on the boundary.
Okay.
Right. So let's sit at this special fixed point in d greater than 3. Let's do large n calculations for the scaling dimension of the order parameter, and then let's send d to 3, just slightly larger than 3. And okay, so these heroic calculations have been done by Ona and Okaba, and to order 1 over n, this is what you get for the scaling dimension, and it's actually, you see that it's proportional. It seems to be proportional to epsilon. That is, it seems to go to 0 as d goes to 3. We don't know whether that's true for the order 1 over n squared term, at least from this calculation, but it's suggestive that as d goes to 3, the scaling dimension of the order parameter at the special fixed point goes to 0. What does it mean it goes to 0? It means that, 0 is like when the boundary is ordered. So this is suggestive of the following, that as d goes to 3, the special fixed point approaches the extraordinary fixed point for large n, and when d hits 3, they just come together and annihilate, such that in d equal 3 at large n, there is only the ordinary fixed point left. So this is kind of some evidence that this is the picture at large n. What about for n just slightly larger than 2? Well, we know that for n equal to 2, we have these 3 fixed points: ordinary, special, and extraordinary log. And these fixed points are some distance from each other. Right, the scaling dimension of the special fixed point, for instance, from Monte Carlo is finite, is not 0, whereas here it's essentially 0. As we already kind of referred to, fixed points do not just appear and disappear. The way they disappear is they collide with each other. But if we just raise n from 2 slightly, we don't. There is no room for these 2 fixed points to collide yet. So we expect that when n is slightly greater than 2, we still have all 3 fixed points intact. So this is again just some arguments. Any questions so far?
I was wondering, when there is the extraordinary in this case, is it still the same as the normal transition?
It's not exactly the same, right? As you can see from this behavior, right? Because for the normal transition, the correlator of the order parameter on the boundary goes to a constant. Here it's decays as a power of logarithm. But you're right, it's almost the same as normal. And if I have time at the end of the talk, I can explain some of the details. It's kind of like normal up to logarithmic corrections.
Thanks.
But logarithmic corrections which are not entirely innocuous. All right, so let's go on. So let me let me first present a sketch of the RG analysis, and if time allows, I will describe the details at the end of the talk. So first, right. So we want to analyze this region of the phase diagram where the surface enhancement is large. When K1 is large, that is when the surface has a strong tendency towards local order. So let's describe the surface order parameter by a vector n, and let's employ a nonlinear sigma model for this surface order parameter. Now let's begin by reminding ourselves what happens if there is no bulk. If you only have the surface, that is, surface is 2-dimensional, so nonlinear sigma model in 2 dimensions. Okay, well, Polikov taught us what happens, right? We have this RG flow for the coupling constant G. We start with G equals 0, that's when, or G close to 0, that's when there is strong tendency towards local surface order, and we let G run. Well, it runs away to infinity. This is indicative of the fact that without the bulk, the surface, the 2-dimensional nonlinear sigma model with n greater than 2 is always disordered. Okay, so this is if we have no bulk. Now I claim that when we add the coupling to the critical bulk, this RG flow is modified, and it's modified in the following way. The coefficient of the G squared term gets modified. So in addition to this contribution n minus 2 over 2 pi that comes from the surface, there is an extra contribution here from the bulk. So then the behavior of the boundary will be determined by the sign of this coefficient alpha. If alpha is positive, then G runs to 0 logarithmically in the infrared, and this is our extraordinary log fixed point. And you can check, from the anomalous dimension of the boundary or the parameter of n, that actually, in this case, the correlation function on the boundary falls off as a power of logarithm with the power expressed in terms of this coefficient alpha. Turns out that to this order, the anomalous dimension is not renormalized by the bulk. Okay, so this is if alpha is greater than 0. If alpha is smaller than 0, then G equals 0 fixed point is unstable. We have a runaway flow. So is alpha positive or is alpha negative? Well, that depends on the value of n. In general, we cannot calculate alpha, but we can calculate it in two limits. First limit is when n is equal to 2. When n is equal to 2, there is only the bulk contribution, no boundary contribution. And this bulk contribution has a definite sign. By the way, I didn't tell you what this S here is. So S is a universal number, and turns out that S is expressed in terms of certain universal amplitudes for the normal universality class. Remember the normal universality class, that's the symmetry broken universality class. So S is related to some universal amplitudes at that fixed point. And yeah, if I have time, I'll explain this in more detail. But S is a universal number. All right, S is a universal number, which is real. In fact, it's positive. So S squared is positive. So when n is equal to 2, alpha is positive. This is the extraordinary log fixed point in the xy case, in the n equal to 2 case. When n is large, one can also calculate alpha, and it turns out to be negative. So that means that as n evolves from 2 upward, there must be at least alpha must have at least one 0. It must switch sign at least once. It can maybe switch sign more than once, but at least once. And I will assume in the rest of my talk that it switches sign just once.
Question at this fixed point. So what's the so the CFT has a marginal operator. So this is a boundary CFT with just the beta function starting at order G square.
So, sorry, at which fixed point?
Yeah, when
extraordinary.
Yeah, when G exactly. The G equals 0 fixed point. What's the?
Yeah, there is a marginally irrelevant perturbation.
Right, and what is this? Some? I mean, what is this operator?
It's just whatever multiplies 1 over G.
Okay. Well. Okay. Okay.
It's like I don't know, like pi to the 4th theory in 4 dimensions.
Right, but do we have? Is there a wiki couple description for this fixed point, which we? I mean, I don't know. We identify. I mean, I guess this is wiki properly. Yeah, okay.
Yeah, maybe asking about what is the G equals 0 fixed point.
Yeah.
When we said G strictly to 0, G strictly 0 is the normal fixed point.
Okay.
And then these are logarithmic corrections on top of the normal fixed point.
Okay.
All right. So what is the critical value where alpha goes to 0? We call it n equal nc. Well, okay, we don't know, I think, is the honest answer. If we just naively extrapolate the large n result down, we conclude that the critical value is around 4. But of course, there are 1 over n corrections here that I have not been able to compute. Another way to estimate NC is to use sum of Bootstrap results that I might discuss later. Just entirely from Bootstrap, we don't have actually enough data for this S, but we can combine some of the Bootstrap information with large N, and that gives NC roughly of order 3. All right. So how does this crossover from small n to large n happen? What happens in the vicinity of NC? Well, what happens in the vicinity of NC will be controlled by the next term in the beta function for G. Right, so near n equal to NC, I can linearize the leading term, the coefficient of the leading term, and physics will be controlled by the sign of this subleading term, by the sign of B. And so far, we have not been able to compute this sign, so we have to consider both scenarios. So first scenario is the sign is positive. So what happens then? Well, then there is a perturbatively accessible, unstable, infrared unstable fixed point for n just below NC, right? And well, the scaling dimension of the order parameter, of the boundary order parameter at this fixed point is small. So the way we interpret this is we know that when n is equal to 2, there is a special fixed point separating the extraordinary log from the ordinary universality class. So we guess that this special fixed point approaches G equals 0 as n goes to NC from below, and then at NC it merges with it and annihilates, such that for n greater than NC, we only have the ordinary universality class left. All right, so this is the first scenario. Second scenario is that B is less than 0. So here the story is more interesting. Here we find a infrared stable fixed point for n just above NC at a finite coupling G, again with the scaling dimension of n being small for n just above NC. So here the extraordinary fixed point moves away from G equals 0 when we go slightly above NC. So we get a fixed point with true power law correlations on the boundary. And we refer to this as extraordinary power. This would be a real boundary conformal fixed point. Now, we know that when n is equal to infinity, there is only the ordinary fixed point in D equal 3 from large n calculations. So we expect that this extraordinary power fixed point must eventually disappear. And we guess that it disappears by again colliding with the special fixed point at a larger value of n, which we call NC2. But in this range from NC to NC2, we have the extraordinary power fixed point as well as the ordinary and the special. All right, so this is scenario 2. As I said, so far we don't know which of these scenarios happens. Scenario 2 seems more exotic, but really, just a matter of the sign of this coefficient. So I think we have to allow for both scenarios. Here's another way to picture the two scenarios. Here is scenario 1. For n smaller than NC, we have the ordinary, the extraordinary log, and the special fixed points. And then for n greater than NC, we only have the ordinary. And in scenario 2, well, we have the ordinary and extraordinary, but depending on whether we are in this range of n or in this range of n, the extraordinary fixed point either has well, this log behavior or true, or is a true boundary CFT. Any questions so far?
Max, what is the mapping between kappa and G? Do you have the approximate map between kappa and G?
I think when well, one can only do it when kappa is very large and G is very small, and presumably just 1 over G is roughly kappa.
But you assume that the map is linear near these funny extra critical points.
I think it will be linear. It's the same. It's the
Landau's
same
theory.
story. It's just purely classical two-dimensional, right? If you ask.
Yeah, you just assume Landau theory basically near the multi-critical point.
That's right. Just fluctuation. You know, this is the stiffness, and you just fluctuations are small there, and you just read it off. Yeah. Does that answer your question?
Yeah, thanks. I mean, probably these coefficients B and A that you don't know, they translate to some well-defined conformal perturbation theory correlation functions, no?
They do, and so for this S, I'll yeah. If I have time, I'll explain how to express S in terms of some conformal bound, some universal amplitudes of the normal fixed points. For B, it's more complicated, but it in principle should still be possible to express B again in terms of some universal data of the normal fixed point. Other questions? Okay. So do we know anything from numerics? So there are two types of numerics available. There is a classical Monte Carlo, and there is a quantum Monte Carlo. That is Monte Carlo and quantum models. And surprisingly, there is very little classical Monte Carlo and even less high quality classical Monte Carlo on this problem. So it's not really settled numerically. So here is what data we have. So here is classical Monte Carlo on the case n equal to 3. N equal to, there is again classical Monte Carlo data. It's consistent with this this phase diagram is verified. The only question is about the precise behavior along this extraordinary line. That I think has to be reanalyzed in view of these findings. But at least the topology of the phase diagram people agree on. For n equal to 3, people don't even agree on the topology of the phase diagram. Well, okay, so here is the Monte Carlo data. So here is from Krech in 2000. So the ordinary universality class, that is the behavior when the surface enhancement is not very large, everyone agrees on. Everyone gets the same boundary exponents. Everything is nice. It's the behavior in the region when the surface enhancement is strong that people don't quite agree on. And in this paper, actually, what the author saw was that the boundary exponent for large surface enhancement seemed to depend on the value of the surface enhancement. And he interpreted it as a long crossover towards the ordinary universality class. It's just because surface enhancement is so large, it takes a long time to reach. So he went with this picture on the left in his interpretation. This slightly later study also looked at something similar to the Binder ratio for the surface order parameter as a function of the surface enhancement kappa here. And what they saw is very suggestive of a crossing in this Binder ratio, and such crossings are indicative of phase transition. So this is actually indicative of a special transition in the case of n equal to 3. If you look at n equal to 2, where we know there is a special transition there, the data near the special transition looks very similar in the Binder ratio. You wouldn't really, from naked eye, be able to tell. But still, people, these authors say nothing about, well, what happens beyond the special transition, what happens at large surface enhancement. Here's also some data on n equal to 4. Again, this is the Binder ratio. Again, it looks like there is a special transition. Again, the behavior at larger surface enhancement is not well characterized. So this is all we know from classical Monte Carlo. What about quantum Monte Carlo? Well, okay, so there's been actually quite a bit of work in the last few years studying a number of two-dimensional quantum spin models with a boundary. So I will discuss, for concreteness, I'll discuss the model in references 3 and 4 here. So consider the Heisenberg model on a rectangular lattice with nearest neighbor spin couplings, but you dimerize the couplings in this way, that the coupling on the red bonds is stronger than the coupling on the black bonds. Okay, so first let's discuss the bulk phase diagram of this model. When JD is very large, the spins on the red bonds just lock into singlets. We have a trivial, well, we have a paramagnetic phase gap. On the other hand, when JD is equal to J, that's just a square lattice Heisenberg antiferromagnet. We know that that has magnetic order, that has Néel order. So we have two phases here, and actually there is a phase transition between them. And kind of from old numerics, we know that this is a phase transition in the classical 3D O3 universality class. All the exponents match. The interesting new findings are about the boundary behavior of this model. And in fact, there are two kinds of boundaries one can consider. First boundary, so-called non-dangling boundary, has boundary spins being part of the strong red bonds, whereas the dangling boundary has boundary spins being part of the weak black bonds. And the boundary behavior in the two cases is different. For the non-dangling edge, the boundary behavior is consistent with the classical ordinary universality class. The scaling dimension of the order parameter matches pretty well. But at the dangling edge, the behavior is very different. The scaling dimension of the boundary order parameter is, and this is the Néel, the magnetic order parameter, the O3 vector, is much smaller, and in fact is consistent with this 1/4 in all of these papers. The geometry considered in the first two papers of the lattice is quite different. So microscopically, the model is quite different in the first two references compared to the last two. But the scaling dimensions are pretty close. All right. So how to explain this? Well, the first thought that people had was, well, at least when we are dealing with spin 1/2, when the spins are spin 1/2 spins, we do expect something new at the dangling edge, right? Because here, even if you go onto the paramagnetic side of the phase diagram, right, you still have this dangling spin 1/2 at the edge. The rest of the spins are gapped, and we know that spin 1/2 chain is well, with translational symmetry, is gapless in one dimension. That's the 1+1D Heisenberg model that's described by SU2 level 1 conformal field theory. So here the boundary is gapless even on the paramagnetic side, whereas we know that for the ordinary universality class, if you perturb onto the paramagnetic bulk phase, the boundary is gapped. So something must be different in the for s equal 1/2 at least, something must be different about the dangling edge boundary fixed point compared to the ordinary universality class. The really surprising finding was that, at least to me it was surprising, was that when people looked at the case of s equal to 1 rather than s equal 1/2, they found very similar exponents at the dangling edge. At the non-dangling as well, but the surprise is it's also at the dangling edge. We know, this is surprising because we know that spin 1 chain is gapped in 1 + 1 dimension. So, for the spin 1 case, there is nothing weird happening on the paramagnetic side. So one would have naively expected both the non-dangling and the dangling edges having the same universality class, but apparently not. And the strange thing is that s equal 1/2 and s equal 1 seem to have the same exponent at the dangling edge. So this is what we know from quantum Monte Carlo. Any questions? So here is well, let me present a kind of a scenario that maybe can explain these numerical findings. So first of all, let's remind ourselves purely in 1 + 1 dimension, what is the difference between spin 1/2 chain and spin 1 chain? Well, the difference in the nonlinear sigma model description comes from this topological theta term for spin equal 1/2, theta equal to pi, for spin 1, theta equal to 0. Okay, so now here is my scenario. So first of all, let's come back to the classical O3 model. And let me assume that scenario 2 is realized in the classical O3 model. Classical O3 model is the model where essentially theta equal 0 in the boundary action. Okay, so let's assume that scenario 2 is realized, that is b is less than 0. And remember, in scenario 2, there is this region with the extraordinary power boundary universality class present. So let me assume that that we have scenario 2, and that moreover NC is just slightly smaller than 3. That is, n equal 3 lies here. Okay? So that would mean that for n equal to 3, for the classical O3 model, there is the extraordinary power universality class with the scaling dimension of the boundary or the parameter being small, because by assumption 3 is close to NC, right? So this is in the perturbative regime where the fixed point coupling G is small. And maybe, maybe that's consistent with the numerics on the dangling edge, because those numerics tell us that the scaling dimension of n is 1/4, maybe 1/4 is small. Notice here one would also have the crossover to scaling exponent would go as n minus nc squared. So this corrections to scaling exponent. So this exponent is small. So this could give rise to some significant corrections to scaling that maybe are important in the classical Monte Carlo, explaining the flow of exponents seen in classical Monte Carlo. All right. Okay. So so far this is about the classical O3 model. How would the analysis change for quantum model with s equal 1/2? That is, how would the analysis change when theta is equal to pi in the boundary nonlinear sigma model? And the answer is, at this level, it would not, right? Remember, this theta term is a topological term, but we are doing perturbation theory in G. So when we are doing perturbation theory in G, it's insensitive to the theta term. So we would have exactly the same beta function perturbatively, and we would end up with the same exponents perturbatively. So maybe this is what explains the similarity in exponents seen in the s equal 1/2 case and s equal to 1 case. Where would the difference between s equal 1/2 and s equal 1 come from? It would come from Skyrmion effects. Well, classically, Skyrmion configurations of n have this action, this classical action. So they're suppressed by e to the minus 4 pi over g. If you just naively replace g by its fixed point value, then this is re-expressing that in terms of the scaling dimension of n. This is a suppression like this, and plugging in the numerical value of delta n, this gives us like e to the minus 8 suppression. Of course, we don't know what the prefactor is, but okay, maybe this is again the reason that s equal 1/2 and s equal to 1 have close exponents. One last comment about this. So I focused on the correlation functions of the null order parameter of the O3 vector. There is also an important O3 scalar in this problem that we know about from physics of 1 + 1d spin chains. That's the valence bond solid order parameter, right? So this is the spin dimer correlation function at momentum pi. We call that valence bond solid order parameter v of x. Now, in terms of the nonlinear sigma model, this VBS order parameter has the same quantum numbers as the Skyrmion density. Well, we know that Skyrmion density is conjugate to the theta angle, and perturbatively in G, the theta angle does not run, right? So that would mean that perturbatively in G, the scaling dimension of the valence bond solid order parameter is equal to 2. Again, up to this non-perturbative Skyrmion effect. So this would be a prediction of the current analysis that scaling dimension of the VBS operator should be close to 2. Okay, so one can. So this is the scenario. This is the scenario for the the Monte Carlo. In principle, one should be able to tune the Hamiltonian on the boundary in the Monte Carlo simulations, and see some of these transitions from the non-trivial physics at the dangling edge towards ordinary universality class. But let me maybe skip this, and let me maybe conclude by saying that I really hope this will lead to more classical and quantum Monte Carlo simulations. I mean, I'm really surprised that we don't know the boundary phase diagram of O3 model in 2020. All right, let me stop here, take questions, and if there is interest, I can discuss some of the technical details about the RG procedure and relation to the universal data of the normal fixed point for those who are interested. Yeah, thank you.
Thanks a lot, Max, for that very interesting talk. So we'll take questions.
I am still a bit confused about this marginal operator, so maybe I'll ask again. Sorry about that. So the fixed point is normal, right? So you said this is the normal transition, and at the normal transition, I thought we do not expect to have a marginal operator. So is this something? So you added a coupling to a vector n, and is the story that okay, this is a two-dimensional XY model, which, okay, it's a free theory at G = 0, so it does have this operator of dimension 2, but it decouples from the normal transition. So we shouldn't look for a solution to the Bootstrap equation in dimension 2 with the marginal operator and the displacement. Is this correct? This is just two decoupled things.
This is essentially correct.
Oh, okay, thank you.
One question. To what extent is it too naive to think that small kappa 1 is like Neumann and the large kappa 1 is Dirichlet?
So for the bulk field, right?
Yeah, because if the Ising interaction is very strong, it sounds very much like it's a Dirichlet effectively.
So actually, it's maybe opposite.
Like I'm trying to rephrase everything you're saying as a flow between Neumann and Dirichlet.
So when dimension is equal to 4, which is the bulk marginal case, the ordinary universality class is Dirichlet, and the special is Neumann.
Okay. So you can try to interpret this picture that you have as a flow between Neumann and Dirichlet.
At least the ordinary and the special, yes. But it's no longer true when epsilon when dimension is smaller than 4. It's no longer strictly true. It's
why? These are like natural conformal boundary conditions, no? Why is it not?
The scaling dimension of
I mean, how can it not be true? I don't understand. Like...
Well, I think it's more useful to think about the OPE of phi of the bulk operator near the boundary, right? And that exponent changes depending on dimension. I don't think it's.
Yeah, but that could just mean that like Neumann boundary condition is not conformal, so it flows a little bit, and then you get what you want.
That's exactly right. So I think the Dirichlet is essentially always conformal, but Neumann is.
Yeah, so the Neumann flows. Maybe you can do perturbation theory around Neumann. Maybe that's a good starting point.
That's exactly how the 4 minus epsilon expansion is done.
Okay.
For the special transition. Yeah.
I understand. Thank you so much.
The problem is that the epsilon expansion does not teach you a lot about the issues I discussed in the D=3 case.
Thanks so much, Max. Nice talk.
So Max, when your paper came out, I was really impressed about the way you set up this RG calculation, because it seemed to me pretty innovative and not something that I've seen before. So how you put together this normal and the sigma model to arrange for the ON symmetry to be restored. So I was wondering if you have any backup slides where you could explain how you actually computed this S parameter, or is it too technical?
Yeah, I'll be happy to explain it. I have the slides here. I mean, it will probably take like 15 or 20 minutes.
Well, maybe we can keep it then for the, if some people have more immediate questions, then maybe we can keep it for an after. Yeah, I'd love to have it a refresher on this, but maybe some other people have more urgent questions. So I postpone this one until, let it be the last question of the day.
Any other questions before we do that?
It looks like we have to.
Sounds like no.
Yeah.
Well, let's. Should we thank Max again, and this is the official end. But now we'll just discuss as long as people want to stay.
Yeah, maybe that's a good idea. So
should I?
Yeah.
Okay, I'm going to stop the recording.
No, why stop the recording? Because this is an interesting part.
Good. Okay.
Because if you don't stop the recording, then you have to hang around, but otherwise you can, maybe you have to go, I don't know.
No, I'll stay. Yeah, okay, yeah, let's just go ahead.
Okay.
So let's thank Max again. Thank you, Max.
Thank you
Nice
again,
talk.
Max. Okay, now we can
Now let's just enjoy this extra explanation.
Okay. So here is the story. Right. So we want to understand this region of the phase diagram with strong surface enhancement. And again, so we use a sigma model for the boundary order parameter, like so. And we want to include the coupling to the bulk critical degrees of freedom. So let's begin in the following way. Let's start with the bulk field phi with an ordinary boundary fixed point. And let's couple it to the nonlinear sigma model, like so, with some coupling S tilde. All right, so this is, and we will be working around the G equals 0 fixed point. So when there is strong tendency of the boundary to order.
And so ordinary or normal?
So we just to set things up, let's begin with ordinary.
Okay.
It will not be useful for any calculations, but just conceptually.
Okay.
Right? So we kind of consider these two layers. One layer is a sigma model. The other layer is bulk with ordinary boundary conditions.
Mm-hmm.
Now, if you work around G equals 0, right, then N has scaling dimension 0, and this coupling is relevant. So we want to understand where does it flow. Okay, so let's proceed as follows. So we will be working around G equals 0. So we, when G is equal to 0, N doesn't fluctuate much. So we kind of parameterize it in terms of fluctuations around the North Pole, if you wish. And let's now begin with just setting G exactly equal to 0. Right? When G is equal to 0 exactly, N does not fluctuate at all. So just a classical vector. So if you have a classical vector coupled to the phi on the boundary, that's exactly like a symmetry breaking boundary field. So that's the normal fixed point. So when G is strictly equal to 0, the theory flows to a normal universality class. All right. So let me fix G equals 0 and N pointing along the North Pole, and let me remind you how the normal universality class looks like. So actually we know quite a bit about the normal universality class, and that's really what makes this analysis possible. So first of all, for the normal universality class, if you look at the nth component of the order parameter of the bulk order parameter, it mixes with identity on the boundary, right? If you think about the OPE, there is an identity in the OPE that comes with some universal coefficient. And then there is a subleading operator. And so this is kind of the longitudinal component, the component along the boundary symmetry breaking field. The transverse components, there is no identity, but there is some operator. I normalize operators to identity as is the convention, and hat denote boundary operators, and no hat means bulk operator. So this is the boundary OP. Now what really allows progress is that we know the scaling dimensions of some of these boundary operators. In particular, the phi hat. This is the transverse the transverse components. The boundary operator has scaling dimension which is exactly equal to 2. It's in fact can be thought as the component of the current corresponding to the symmetry breaking generator. We know the current has scaling dimension 2, in the bulk, and then you just take the normal component of that current near the boundary. That's what phi hat I corresponds to. All right. And then this operator sigma hat, the subleading operator in the longitudinal component, is thought to have dimension 3. This is thought to be the displacement operator. This is the lowest on minus 1 singlet on the boundary. It's not very crucial that it has a dimension equal to 3 exactly. What's important is that it has a dimension that's larger than 2. But it's thought to be the lowest thing here is thought to be the displacement operator and to actually have a scaling dimension 3. All right. So any questions about this so far?
So the fact that in this normal universality class, the symmetry on the boundary is explicitly broken. So what does it mean for the conservation equation for the bulk current? So it just
right. So in the bulk, the current is still conserved.
Yeah.
So the reason that this phi hat has a scaling dimension 2 is exactly the same reason that the displacement operator has a scaling dimension exactly equal to 3. Right? You have a symmetry that's exact in the bulk but broken on the boundary, and so the displacement operator is essentially TDD, or T normal taken towards the boundary, and this phi I hat is essentially the bulk current corresponding to the broken symmetry, the normal component of that taken towards the boundary. Normal, I mean the direction normal to the boundary.
But suppose then that the symmetry was not broken explicitly on the boundary. What would be different in these OPEs?
That's right. So now this is the next step. All right. So far, I fixed G equal to 0, and I picked the direction of n along the North Pole. But I would eventually like to allow n to fluctuate around the North Pole, even if just a little bit. So still working with G equals 0, I can say, okay, what if n doesn't point exactly along the North Pole, but a little bit away from the North Pole? Okay, you can just say that, now you will generate normal, you will flow to normal boundary conditions with symmetry breaking field slightly tilted away from the North Pole. But that's not very convenient, right? You do not want to use different boundary condition every time you change the direction of n slightly. So it's more useful to just say, okay, we flow to normal universality class for phi with a symmetry breaking field along the North Pole plus a perturbation. What kind of perturbation can we write down? Well, the simplest thing consistent with the remaining ON-1 symmetry is like this. We couple the transverse components of n with the transverse component of the boundary field phi. Right? So this is sum from I equal 1 to n-1. Now remember, this phi I hat is the leading operator in the OPE of the transverse component of the order parameter. Okay, so this is the lowest dimension coupling that we can write down. There is a simming problem with this, which is that this this action only has an explicit ON-1 symmetry. It doesn't have an explicit ON symmetry. If we try to write down, this only has the coupling of the transverse components of n and the and phi. If we try to couple kind of the longitudinal components, well, we know that sigma hat, the leading longitudinal operator here, has dimension 3, so this coupling would be irrelevant around the g equals 0 fixed point. So we are stuck with this. So somehow it must be that this action has a hidden ON symmetry, even though only ON minus 1 is explicit. And I claim that actually only has that symmetry for a particular value of S. For S given by this ratio of the universal amplitudes A sigma and mu phi of the OPE coefficients. So let me explain where this comes from.
This is in the limit g going to 0 or g exactly 0?
That's a good question. So it's certainly true for g exactly 0, but I think it's more than that. So what I'd like to say is that there is, I should be able to write, there are actually infinitely many terms that should be written here. And those terms, for instance, in addition to this operator, also include pi squared multiplying this whole thing, right? Where pi squared is pi j, and it's higher order. So in fact, you should multiply this by some function of pi squared. And we'd like to restore the ON symmetry order by order in pi. And you can think of that order by order in pi as order by order in G. Does that sound reasonable?
I guess, yeah. Thank you.
Yeah. So let me explain where this equation comes from. So this is still, let's still work with G equal to 0 exactly. So, okay. So we know that when the symmetry breaking field N points along the North Pole, the order parameter in the bulk has this expectation value. If we tilt it away from the North Pole a little bit, well, the expectation value should rotate, and the transverse component should acquire an expectation value, like so. Right. On the other hand, we should be able to use this coupling and to compute this transverse component perturbatively in pi. Here is what we would get. We would get this correlation function of 1 phi in the bulk and 1 phi on the boundary, computed with at the normal boundary fixed point with the boundary symmetry breaking field along the North Pole. But this correlator is actually exactly fixed by conformal symmetry, like so. So we can do the integral and match to this expression, and that fixes S. All right, so this is really the main crux. Yeah. So we see that S, this coupling, is expressed in terms of the universal amplitudes at the normal fixed point. It's not the same as this S tilde. S tilde is some non-universal coupling that we start with, but at the end of the day, S is dimensionless and is universal. All right. So what is the value of S? Well, we need to know these two amplitudes, A sigma and mu phi. And one can calculate them in the large N expansion, for instance. Here is that result. Going to order 1 over N, it's a little painful. Actually, all the Details of the calculation are explained in this paper by Ono and Okabe, but for some reason they don't give the final answer. So, so it took me like several weeks to get this number. But anyway, so here's here's the large n. You can also do epsilon expansion for these quantities, but turns out that if you just go to first order epsilon correction and plug in epsilon equal to 1, you get some nonsensical results. So doesn't seem very useful. There's also some bootstrap data for a sigma, not for mu phi so far, but for a sigma there is some bootstrap data for n equal to 1, 2, and 3. And you see that the bootstrap for small n doesn't look anything like the large n. The large n is the blue curve. So either so maybe the behavior is non-monotonic. That would be very interesting. Not sure what else to say here. Right. So okay. So here's what we know about S. Now, how do we use this? Well, now we have our action, so we can run with it, and we can do a renormalization group. So we can calculate how the coupling constant G renormalizes, and well, we just do perturbation theory in pi, which is the same as perturbation theory in G, and at the leading order, the only new diagram that contributes, in addition to the diagrams coming just from the nonlinear sigma model action, is just this very simple diagram with which involves a 2-point function of boundary field phi hat, and because the 2-point function is fixed, we know everything about this. So that's where this extra contribution to the running of G comes from, and well, that's the story. Now, I would be very skeptical about this story myself, because this restoration of symmetry, a little strange. But
sorry, okay. This restoration of symmetry, I mean, why is it suspicious? It looks a lot like what I don't know, in high energy sometimes it's called Stuckelberg procedure or something like that. So this phi I is the answer of the theory at the normal fixed point for a rotation, right? If you perform a broken ON transformation, you get in the action phi I. That's the definition of the field, with a coefficient which is the angle by which you rotate it. And so what you did is to essentially promote that coefficient to a field and then give it a kinetic term, which is sort of I mean, it's of course is very interesting in this context, but it seems like a established, like a sensible thing to do.
I'm sorry, Marco, but have you ever seen anywhere that we fix? I have never seen anywhere the argument where you have to fix a coupling from the condition that the action should have some hidden symmetry.
I mean, that I think should follow from the normalization of this phi. It's the fact that phi appears with this, right? This phi hat as a natural normalization in terms of the current, while here it's normalized to 1. So, right, it would be like in the stress tensor, if you did a diffeomorphism and you normalize the stress tensor to 1, you wouldn't have del G mu nu T mu nu, but you would have something that involves CT in front. And then if you wanted to introduce a metric in that way, I mean, I'm not saying it's trivial or anything like that. I'm just saying it makes a lot of sense. It seems like the only thing you could do to restore the symmetry from to restore the symmetry starting from a fixed point that has less.
So you are saying you know how to write this argument in a way which does not require fixing any constants by doing any integrals.
Well, the integral I've done before, right? This procedure of fixing the normal, these integrals are exactly the same you would do to fix the normalization of this phi hat, right? So you've done them, And you have like, it's exactly in the same way in which normalization of T mu nu is fixed by requiring that it matches the variation of correlation functions. Like it's a word identity in the same way. So these integrals must be done, but okay, you could do it before or after. I mean, I'm just trying to make this look normal, not
No, okay. So you have some intuition about that. That's great. Yeah.
I think, you know, one example of something somewhat similar that I know is, say, in Fermi-liquid theory, right? If you do, if you want to restore Galilean invariance, in Fermi-liquid theory, you obtain some relation between the effective mass and the coefficient and the Landau parameter F1. And again, you know, Galilean symmetry is not apparent in the action, but you kind of restore it. So that's one place. Again, I think in both of those examples, you have to kind of do it order by order in whatever. In the Fermi-liquid theory, that would be in the energy. Here, it would be in pi. So here, you know, one thing I didn't mention is, for instance, there is also a just pi squared term that you have to add to the action to restore the ON symmetry, just a mass for pi. You know, you generate one from this 2-point function. Again, it's not so unusual, for instance, even in the just ordinary 2-dimensional nonlinear sigma model. If you're not super careful with your regularization, you will end up with a mass for pi that you then cancel away with the counter term. So essentially, you know, there is going to be an effective, at higher orders, there is going to be an effective potential V of pi squared, and there is going to be some function f of pi squared multiplying this term, and you have to kind of fix those two functions order by order by insisting on the ON symmetry. Yeah, but what I started with, you know, my doubts about this procedure were somewhat alleviated by the following observation, which is that you can do you can repeat these calculations in dimension slightly larger than 3. So go to d equal 3 plus epsilon. And the way things change to leading order is that you have an extra contribution to the running of G, to the beta function of G, that looks like this. So then, if alpha is negative, that is, if n is greater than nc, you get a perturbatively accessible infrared unstable fixed point that we can identify with a special transition. So first of all, you know, if d is greater than 3, then there is an extraordinary fixed point, g equals 0. G equals 0 is stable, and you know, g runs to 0 as a power law at that fixed point. So that really means that this is really the equivalence of the extraordinary and normal fixed points when dimension is greater than 3. The nonlinear sigma model essentially decouples from the bulk with normal boundary conditions. So that's the extraordinary fixed point. But we also have excess for d equal 3 plus epsilon for n greater than nc to this special fixed point, and you know, this is the fixed point coupling, and this is the scaling dimension of a boundary or the parameter. And okay, so let's take d equal 3 plus epsilon, and let's take n large. So when n is large, we know what s is equal to, right? Because we've calculated the two amplitudes in the large n limit. So now we can calculate the scaling dimension at the special fixed point for large n and small epsilon. And okay, so here's what we have. This is the value of alpha at large n. We plug in, to here. This is what we obtain for the scaling dimension. Notice exactly, the structure is such that it goes to 0 as epsilon goes to 0. I already alluded to this earlier in my talk, but now we kind of know it to all of that all the higher order terms here, order epsilon squared, order epsilon cubed. So this is from RG, from our RG procedure. Our RG procedure with the value of S taken from large N expansion. And now you can compare this to direct large N expansion. So you can set D greater than 3, do large N, then extrapolate D back to 3 plus epsilon. And that's what Ona and, using the results of Ona and Akabe, we actually get the same thing to the present order. So the two calculations are quite non-trivial. The calculation in Ona and Akabe is you sit at the special fixed point, you do the large N, and then you take D. They can do for any D, but you take D to 3 plus epsilon. Here, in our calculation, we do randomization group. The large N input that we use is the value of these amplitudes at the normal fixed point computed with large N expansion. Quite kind of technically somewhat different procedure, but we get the results to match. So I think this is what convinced me that actually this RG procedure is probably correct. Yeah. Any questions? All right, so I think those are all the details.
Okay. Thanks, Max.
Thank you.
Thanks.